Section 1.3, Precision and Accuracy in Calculations. So our objective for this lesson is to report quantities with accuracy and appropriate levels of precision. So first we need to distinguish between these two words, accuracy versus precision. So you noticed in the first video that accuracy really has to do with how close it is to the actual value. So accuracy is the closeness of the measured value to the actual. Okay. So if you are accurate, that means you are close, if not right on the correct or exact measurement. Okay. So if I'm measuring a 10-pound weight, if I measure it with a scale and my scale says it's 9.9 pounds, that is very close. That is very accurate because it's very close to the actual weight. Whereas precision is the level of detail of the measurement, determined by the smallest unit or fraction of a unit that can be reasonably measured. So basically, precision involves comparing measurements to each other. Okay, or we'll go ahead and get that book definition. The level of detail of a measurement okay, and that's usually determined by the smallest unit that can be measured. Okay, so precise measurements don't necessarily go with how close it is to the actual measurement, but more so how close it is to each other. Okay, so for example here, I've got 3 targets down here. This first one is not very accurate because all the points are kind of scattered all over the place. And it's also not precise. So it's not accurate because these are not close to the actual target, which is there in the middle. And it's not precise because they're not close to each other. So this is low accuracy and low precision. Okay. Whereas this next one, no, they are not close to the target, but they're all close to each other. There's this nice little huddle. So there is low accuracy because it's not close to the target, but it has high precision. The thrower is quite precise in that they're getting them all in that same area. Okay. This next one, they're all pretty close to the target, so that would mean it has high accuracy, but they're really not close to each other. If I was to measure this one far away from this one, those two are pretty far apart, so that we would call that low precision. Whereas this next one, they're all close to the target and they're all close to each other, so this last one is high accuracy and high precision. Okay. So to help determine the precision of the measurements is you really need to know what tool are you using to measure and what's the smallest unit that it can measure. Okay, so here, for example, if we're measuring this beetle, okay, if we notice what units we're using to measure, so let's go ahead and notice. First, it's centimeters. And this tells me this is 1 centimeter and this is 1.5. So that tells me that each one of these, so if that's 0.5, then this means this one is 0.1, 0.2, and so on. 0.3, 0.4, so 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so it looks like the smallest measurement on here the smallest measurement is 0.1 of a centimeter. Okay, So that's the most precise that we can be. We can't be any more precise than that. So meaning that if I look at this measurement, we zoom in here, this beetle looks like it falls in between, here's 1, so this would be 1.1, 1.2, 1.3. It falls in between 1.2 and 1.3, but I can't say 1.25 because I don't have a measurement for that. I have to round at this point and look at which one is it closer to, 1.2 or 1.3. It looks like it's smack dab halfway, which means we round up. So I would say this measurement is 1.3 centimeters. Okay. So this is my reported measurement. This is what I report it as. But again, there's always that measurement error. There's always a bit of error. So to determine how much error there could be that means that this measurement of this beetle could really be half a unit either way. So a reported measurement and the actual value of what was measured can differ by as much as half the unit of measurement. So I would take this 0.1 and take half of it, which is 0.05. Okay, and really I could be 0.05 on either side of it. So that tells me that my actual measurement could be anywhere between 1.25 and half a unit the other way, 1.35. So I know this beetle is actually 0.05 on either side of the measurement that I got. So we take the smallest unit of measure, which is 0.1, take half of it. So if you don't know what half of that is, you can always divide it by 2, right? Take 0.1 divided by 2. See what I get, 0.05. So really I could be 0.05 of either side. So subtract, so basically I took this 1.3 and subtracted 0.05 to get that one. And then I took the 1.3 and added the 0.05 to get that one. So really I know my measurements in between those two, the actual for real measurement of this beetle. Okay, regardless of my, so there, that takes into consideration there was some measurement error there, meaning maybe it was a little closer to 1.3. There's that bit of error there. Okay, so here we look at another one. So you can only be as precise as the device you're using. So here we're measuring this ribbon with 2 separate devices. We have first the yellow. We have the yellow tape measure up here. The only marked off units are centimeters. So I can only measure to the nearest centimeter. So I have to look, and looking at this yellow ruler, it looks like this one's closer to 5. So using the yellow ruler, I would say 5 centimeters. Again, that's my reported measurement. The actual measurement could be anywhere between a half of that. So it could be anywhere from 4.5 to 5.5. That's the range in between. I measured it as 5. Okay. Hey, whereas this blue ruler, if you notice, is measured in millimeters. So we've got 10, 20, 30, 40, 50, but it also has 1, 2. So this one measures much more much more precise. The precision here is much more precise. So we come look here. If this is 40, then there's 45 right there in the middle. 46, 47. It looks like it's almost right on 48. So I had 48 millimeters, which if we divide by 10 to get to centimeters, there are 10 millimeters in 1 centimeter. So we could divide this by 10. So that's equal to 4.8 centimeters. Okay, so again, more precise measurement here than here. It just depends on what tool are you using to measure. But again, it could go half a unit of measurement in either way. So the smallest this measures is 1 millimeter. So this is anywhere from 48.5, sorry, wrong way, 47.5 to 48.5 millimeters, or 4.75 to 4.85 centimeters, depending. So this is that's my window of error It could be in between those two, but this is my reported measurement. The actual measurement could be anywhere between 47.5 and 48.5. Okay, because we do that. Okay, significant. Next, we're talking significant digits, which is normally talked about in science. It also has that mathematic component to it. Okay, so a significant digit is a digit in the measurement that carries meaning. Digit in the measurement that carries a meaning. In terms of precision. Okay, so basically it is, what part of the measurement actually has some meaning there. So here's our rules for significant digits. All non-zero digits are significant. So for example, over here, 4.3161, those are all non-zero. There's 4 of them, so that's 4 significant digits. 295 has 3 significant digits. Zeros between. So if we have zeros between 2 significant digits, they're significant. Okay. So for example, the number 305, the 0 is significant. But zeros at the end of a number, at the end of the number to the right of the decimal point, are significant. So if it's on the end, but after a decimal point, it's significant. If it's at the end, but in front of a decimal point, it's not significant. Okay, so I'm going to kind of jump down here. So for this number, 94 million, those zeros are not significant because there's no decimal there. Okay, so but zeros to the left of a non-zero digit in a decimal number. So if your number is less than 1, meaning if you only have zeros in front of the decimal, then the zeros after the decimal are not significant. Here, I had a 4 in front of the decimal, so these numbers after are, but these in between numbers here are not. So like the 0, 0, 0 are not, the 0 is not. Because those are just, if it's a place, if it is a just placeholder to give the number its correct place value, then they're not significant. Okay, like these ones or these ones. Whereas this doesn't change the place value of the 4 and the 1, so they are. This 0 does not change the place value of the 9, the 4, 0. So it is. Okay, these zeros, if I was to remove them, they change the place value. So they're not significant. Okay. I hope that made sense. So just always refer back to this table. And the more we do these, the better you'll get with those significant digits. Okay, so here if we look at this table, let's go ahead and let's count which ones are significant. Okay, so first of all, this first one, let's double check, has 3 non-zero, so it's got 3 significant digits. This one has 2 non-zero numbers. This 0 is in front of the decimal, so it's not significant. That's got 2 significant digits. So a lot of times what I like to do is I like to take a different color marker and like kind of mark the zeros that are not significant. That's one's not. Okay, this next one, these last 2 zeros are not significant. These ones in the middle are, because they're holding that place between the 2 and the 3. So this one has 1, 2, 3, 4, 5 significant digits. These are not significant, so that one only has 1. Since this has a decimal, all 3 of these are significant, so it's got 4. This one, this last 0 is not. Oh, it's after the decimal. Ooh, missed the decimal. Sorry, I thought that was a comma. Okay, I missed the decimal. Yep, everything in this one is significant because it's after that decimal point. Okay. So let's go ahead. We're going to skip this. Your turn 3. Okay. So when it comes to calculating with significant digits, when you're multiplying your result, you should always give your answer. You should always round to the same number of significant digits with the fewest significant digits. So look at the significant digits of each number that you're multiplying. Which one's the smallest, and that's how many you should round to. Okay. In addition to subtraction, it should be given with the same precision as the least precise value. So if you have one value that's rounded to the nearest centimeter, then your answer needs to be rounded to the nearest centimeter. So the least precise, okay? For example, Lisa is measuring a poster that she wants to frame. She finds the length of the poster. So I'm going to sketch a poster. Always a good idea, guys, to sketch a picture and label stuff. The poster's width is 32 centimeters. I'm going to look there. That has two, what we call sig figs, significant digits. Significant figures, we use sig figs. We kind of shorten it that way. And this is 45.6 centimeters. That one has 3 significant digits. What is the length of the frame? So I want to know the length of the frame all the way around. So what is this length of my frame? How much framing material do I need? So let's go ahead and let's do the length of the frame first. So we're going to have to add them all up. 45.6 plus 32 plus the other side over here, which is 45.6, plus this other side, which is 32. Okay. So here I'm adding. If I add them all up, I get 155.2, but I have to round it to the least precise. The least precise here would be this 32 centimeters because it's just whole centimeters. So I need to round this to the nearest centimeter, which would round to 155 centimeters. The least precise, since I'm adding. Next, I want the area. Area of the glass, so the glass that covers it in here. So to find the number of square units it would take in there, I will need for the area, I need to multiply the length times the width. When I multiply these two, my calculator gives me 1,459.2 centimeters. But when multiplying the fewest significant digits, this one only has 2. So I have to round this to 2 significant digits. So I would round to these first 2 places. So 1459.2 would round to 1,500 centimeters. And I can't put a 0.0 because that'll give it too many, and squared because it's area. Sorry, centimeter squared. Because that's area. I have to round it to 2 significant digits because that's the most significant digits that I have in any of my answers. Okay. All right. So now I want you to go ahead and do this one. Suppose you use the perimeter formula. There's another version of the perimeter formula right there. Another way to find perimeter. To calculate the length of your frame. Does the presence of the 2's in the formula have effect on how the length of the frame should be rounded? Explain. Okay. So pause the video and do that your turn 4. Example 5. Average speed is the distance traveled divided by time. So to help me remember this, average speed is the distance traveled divided by time taken to travel, is I always remember that when I'm driving, let's say I'm going 65 miles per hour. This unit here, this right here tells me what to do for speed. It's miles divided by hours. So this is my speed. My speed is the miles divided by hours. The distance traveled divided by time. Miles is distance, hours is time. Hey, so here we've got 2 different methods for finding the average speed of the dog walker. So here, if you notice, they give us some information over here. They tell me that at time 1, she's 3.3 seconds in, and she's gone a distance of 33.7 miles. At 11.2 seconds since she left, she's at 66.4. Sorry, that's meters, not miles. I'm like, that's a really long way. It's meters. We're dealing in meters here. M is just meters. MI is miles. So down here is a green box that shows 2 different ways of doing it. One is average speed. So for distance, we took what is her change in distance. So they took the 66.4 minus the 33.7 to figure out how far did she go from here to here. How far is that distance? That's this first bit. And then how long did it take her, the change in time? So she was at 11.2 seconds here, 3.3 seconds here. So they figured what's the difference between those two? It took her 7.9 seconds. And then they divided. After they divided, they got this long decimal. But since this is a subtract and a division, we have to look at significant digits. The smallest significant digit is 2 with that 3.3. So we had to use 2. So we rounded to 4.1. Okay. Here is another method. They did it as basically 3 separate problems. They did the change in the distance, 66.4 minus 33.7, and then rounded it to 2 significant digits, 33. Then they did the change in time, rounded to 2 significant digits, 7.9. And then they divided the 33 and the 7.9, got 4.117, and rounded to 2 significant digits again. I want you to notice that this was the answer. They rounded here. And then this is the answer. They rounded again. And then this was the answer, but then they had to round again. This, each time you round, you introduce error, or your answer is less precise every single time you round. Doing it this method, we only rounded once here at the end. Okay, so that's what makes this one the preferred method. And with our calculator skills now, we can do this whole process in our calculator. I would take this first part, put it in parentheses. The second part, put it in parentheses, and then divide to show you. So with my calculator, I would do parentheses. I would do parentheses, and I would do that first bit, the 66.4 minus the 33.7. Close the parentheses. There's my top. And then divide it by, now in parentheses again, my denominator, 11.2 minus the 3.3, close parentheses. There's my final answer, and now I round to 2 significant digits. Okay, so we call that round off error. Explain why. Because you rounded 3 times. Because it rounded 3 times in one problem. And we want to avoid doing that. We want one single rounding at the end.